So today we will see hexagonal close packed crystal structure HCP. So before that let us have a recap of a few of the important crystal structure terms which we had seen in our earlier lecture. First one is coordination number, which is the number of equidistant nearest neighbor atoms of an atom in a particular crystal structure, that is number of atoms in the close proximity, coordination number. And we have seen in the case of simple cubic crystal structure, this coordination number is found to be 6. In face centered cubic crystal structure, coordination number we got 12, and in body centered crystal structure we have seen coordination number is 8. Then we have seen nearest neighbor distance. Nearest neighbor distance is distance between two immediate neighbors. So when in hard sphere model, when we work out, these two spheres will be in contact, so that this nearest neighbor distance is distance between the centers, so that this will be radius plus radius, that is nearest neighbor distance is 2r. Therefore radius will be equal to nearest neighbor distance divided by 2. Then we have seen atomic packing factor. This atomic packing factor talks about what percentage of the unit cell volume is occupied by this hard sphere or solid atoms, or how much is vacant. Vacant space we call void. So it gives an idea about the packing density, whether it is closely packed or loosely packed. So that is what atomic packing factor. In the case of simple cubic crystal structure, atomic packing factor was found to be 52.4%, and in the case of body centered cubic crystal we have seen it is 68%, and in face centered cubic crystal we have calculated atomic packing factor which was 74%, and 74% is the closest packing, that is when hard spheres are packed in space. If we cannot occupy the entire space, there will be some empty space, that is the space occupied by the atoms, that is what we call it atomic packing factor. And this atomic packing factor in the case of we got it 74% for a face centered cubic crystal. This 74% atomic packing factor in the case of that face centered cubic crystal is considered as the closest packing. So therefore it is also known as cubic close packing. So this face centered cubic crystal is also known as cubic close packed crystal structure, because the packing is found to be the highest or the densely packed form. And then next we had seen number per unit cell, number of atoms per unit cell and their lattice positions. That is in the case of simple cubic crystal structure, the number of atoms per unit cell was found to be 1. Simple cubic crystal structure, this was found to be 1, and it was given the lattice position 0, 0, 0. Whereas in the case of body centered cubic crystal, this number of atoms per unit cell was found to be 2, and it was given lattice positions 0, 0, 0, 0, 0, 0 and half, half, half. This half, 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 this is known as body centering translation. So by repeated application of this body centering translation on lattice points in body centered system, you will be able to reproduce or realize the complete space lattice. In face centered cubic crystal we have seen that is number of atoms per unit cell is 4, and the lattice positions are FCC, it was 4, lattice positions are 0, 0, 0, then another one is half, half, 0, then next is half, 0, half, and this is 1, this is 2, then one more 0, half, half. So these three are known as face centering translation. By repeated application of these three translations on any of the lattice points in face centered cubic system, we will be able to reproduce complete face centered that cubic crystal structure, or space lattice can be completely reproduced. So that is number of atoms per unit cell. Then one more interesting term is second neighbor distance. So in the case of simple cubic system, we had seen This is our simple cubic crystal structure or unit cell. So, if you take any particular lattice point, then this will be having nearest neighbor distance, this is 1. So, along x direction we will have 1 in this direction, 1 here. Similarly, along y direction we will have 1 up, 1 below, and in z direction also we have 2. That is what we have seen, this coordination number 6. But second neighbor distance is, if you take one corner point, then this face diagonal distance is considered as the second neighbor distance. So, along this face diagonal, if we consider for this one particular atom at this corner, one face diagonal comes here, one face diagonal goes here, the next adjacent unit cell, and one face diagonal comes here, one adjacent here, and one face diagonal comes here also. So, altogether that is in one plane there will be 4 second neighbors. Therefore, xy plane, xz plane and yz plane there will be 4 each, and therefore, second neighbor distance in the case of simple cubic system will be 12. In face centered system, if we take, so this is our cubic structure. And I am just taking one atom, that is the only front face. So, here front face there is a atom at the center. So, all the lattice points are identical in a particular space lattice. Therefore, if you take this one, there will be 4, this is one corner point, this is 1, 1, 1. This is the nearest neighbor distance, and accordingly we have taken 4 in one plane and then 3 planes, 4 each, then coordination number was found to be 12. But in this case, second neighbor distance, when we take, this is the shortest distance and this is the next higher distance. Therefore, if you take this one corner point, this is the second neighbor distance. Therefore, along x direction there will be 2, y direction there will be 2, and z direction also there will be 2. Same is the case with body centered cubic system. Therefore, in face centered and body centered cubic system, second neighbor distance, second neighbors will be, number of atoms in the second position is that is 6 each. So, 6, 6 and 12. So, this is for body centered system, this is for face centered system, and this is for simple cubic system. So, some of the examples for these 3 cubic systems are, in the case of simple cubic system crystal structure, it is comparatively almost nil. There is only one example given, that is alpha polonium. So, alpha polonium is the only material system crystallized in simple cubic structure. In body centered cubic system, body centered cubic crystal examples are sodium, chromium, alpha iron, molybdenum and tungsten. And in FCC, examples are calcium, copper, gold, nickel and silver. So, these are examples for simple cubic crystal structure, body centered cubic crystal structure and face centered cubic crystal structure. So, the cardinal principle of crystal structure is that there is lattice plus basis is equal to crystal structure. That is, atoms in the crystal are attached to either Bravais lattice points or some points which have some fixed relation to these Bravais lattice points, and that gives us the crystal structure. This simple cubic, face centered cubic and body centered cubic crystal structure, they are the most basic type where the basis consists of only one atom. So, today in our discussion we are trying to go the next step, that is the basis consists of 2 atoms each. So, that is what we are going to see, that is hexagonal close packed crystal structure. So, in hexagonal close packed crystal structure there are many metals crystallized in this hexagonal close packed crystal structure. Example, we have cadmium, zinc, cobalt, magnesium, titanium. So, these are a few examples for hexagonal close packed crystal structure. So, in hexagonal close packed crystal structure, it is formed by attaching 2 atoms bases. Bases consist of 2 atoms each to hexagonal Bravais lattice. So, when 2 atoms are attached to hexagonal Bravais lattice, we will be getting 2 atoms per unit cell, and that will be packed in a closed form. That is what hexagonal closed packed crystal structure, which we have to discuss. But before going for that, we will try to understand the packing in 1, 2 and 3 dimensions. So, here we discuss hard sphere model. So, hard sphere model means the atoms are considered as spherical hard structure. So, if we are packing these hard spheres in 1 dimension, for tight packing, so we will be arranging these hard spheres in contact along 1 direction. So, this is packing in 1 dimension. So, if we have atoms arranged like this, and if you take any particular atom, this atom is in contact with 2 other atoms. So, here 1 atom and here 1 atom. So, here is 1, 2. So, therefore, its coordination number will be 2. Coordination number is 2. This packing in tight packing in 1 dimension. Second case is packing in 2 dimension. So, when this closed or when these hard spheres are packed in 2 dimension, we have got 2 options. One is these type of 1 dimensional packed layers, they will be placed one over the other. So, that means the second layer will be coming something like this. Suppose we have got a second 1 dimensional layer which is packed like this. So, in this case, so one atom is just over the other. So, this is actually a loose packing where large space will be going vacant, empty space will be there, and that is void will be big in size. And in this case, if you take any particular atom, here, this particular atom is in contact with 4 atoms, 1, 2, 3, 4. So, there are 4 atoms with which it is in contact, therefore, its coordination number will be 4. Coordination number will be 4, and if you connect these 4 atom center points, so this will form a square. So, this is called a square packing, but this will be a loose packing and coordination number is 4. But we are interested in tight packing. In tight packing, we will be taking these 1 dimensional layers. So, this 1 dimensional layer, one layer will be placed over the other, that is the way it is packed. In that case, the particles or constituents in the second row will be seated in the gap or the dip formed in the first row, and similarly third row particles will be seated in the dip formed in the second row, and like that it will be layered. In that case, the packing will be very tight. That is what we have to see. Here, this is one dimensional 1 packing or 1 layer. Then second one, this dip, the particle of the second layer will come. So, here we will be having 1 particle. This point will have another one. So, these particles will be in contact, and here we will have another one. Here we will have another one, and the next one will be here. So, we take 5 particles in each row, and the next one, third row will be coming here. So, here 1 particle will be coming, then here 1 particle will be coming, here 1 particle will be coming. This is the way it is packed. So, in this packing, this is a tight packing and maximum space will be occupied, and this connection, this point where these 3 particles are in contact and there is some empty space, this point is called void. It has the shape of a triangle, and this void is called a triangular void. And if you take any particular particle, it is in contact with 6 immediate neighbors, 1, 2, 3, 4, 5 and 6. So, its coordination number will be, coordination number is 6, and if you connect these 6 centers of these 6 particles, so you will be getting a regular hexagon. And this is known as hexagonal close packing in 2 dimension. This layer number 1 and layer number 3, they are aligned identically, whereas layer number 2 is aligned differently. That means even numbered layers will be aligned identically and odd numbers layered will also be aligned identically, but it is different from the alignment of second or this even numbered layers. So, this is how we are getting close packing in 2 dimension. The third one is 3-dimensional packing. In 3-dimensional packing, these type of 2-dimensional layers will be stacked or layered one over the other. Again, in such a way that these projections will be seated in the dip formed in the first layer. So, first layer or second layer will be seated comfortably perfectly into the dip formed in the first layer, and third layer will be placed in the or seated in the dip formed in the second layer, and so on. So, in that case we will have again like this, first and third layer will be aligned identically, second and fourth layer will be aligned identically, like that fourth and sixth layer will be aligned identically, but these even numbered layers and odd numbered layers, their alignment will be little different. So, there will be an alternate alignment. So, we call it, there is 2, so assuming this type of layers are there behind the board as well. So, then that will be a 3-dimensional packing. Then this we can call A layer, this is B layer, then there is A layer and again B layer, like that it will go. And this type of packing is called AB packing. So, in this AB packing, there are 2 possibilities when they are packed. One possibility is triangular void in the first layer and the second layer are coming one over the other, then a new type of void will be formed. That void is called octahedral void. Octahedral void. So, around that octahedral void there will be 6 atoms, that is 3 atoms from the first layer and 3 atoms from the second layer. So, where these dip that is they are placed in such a way that the triangular voids come in contact. Another possibility is on the triangular void of first layer an atom of the second layer will be seating. So, in that case again that triangular void, that void region will be modified where there will be 4 atoms coming in contact. That type of void is called tetrahedral void. So, in tetrahedral void there will be 3 atoms coming like this in one layer and over which another atom will be coming like this. So, this blue is coming from second layer and this red is coming from first layer. So, one triangular void is covered by an atom from the upper layer, whereas in the case of octahedral void we will be having like this. This is one here and here there will be a gap. So, here there will be another one and like this. So, we will have these one triangular void will be coming in contact with another triangular void and there 6 atoms will be that is immediate that is will be in contact with that void, whereas here 4 atoms will be in contact with that void, or that void will be shared by these 4 atoms, and this is called a tetrahedral void and this type is called octahedral void, and we are interested in this tetrahedral void for some calculation. So, now we have that hexagonal close packing. So, hexagonal close packing is actually it is a close packing of hexagonal Bravais lattice which is having 2 atoms per unit cell. So, normally hexagonal Bravais lattice is defined, that is A is equal to B but not is equal to C, and alpha is equal to beta is equal to 90 degree and gamma is equal to 120 degree. This is our hexagonal Bravais lattice. So, in this case if we draw it, so this is your B, this is C and this is A. So, A is equal to, this is B and this is A. A is equal to B but not is equal to C. So, this is So, this is our hexagonal Bravais lattice, and this angle is 120 degree. So, here if you take it like this angle will be 120 degree. And normal hexagonal Bravais lattice, each corner point there will be one atom, therefore, the number of atoms per unit cell will be only 1. In the case of hexagonal close packed system, this hexagonal Bravais lattice will be having 2 atoms per unit cell, because the bases consist of 2 atoms each. So, these 2 atoms in the unit cell, they are having lattice positions, they are 0, 0, 0, and the second one is 2 by 3, 1 by 3, 1 by 2. So, this 2 by 3 and 1 by 3 even we can interchange, that will not create any trouble, because there are 2 equivalent positions. So, these are the 2 lattice positions, one is 0, 0, 0 and 2 by 3, 1 by 3, 1 by 2. So, 2 by 3, 1 by 3, 1 by 2 means, so this is our axis, this is B axis, this is A axis and this is our C axis. Along A direction we can go 2 by 3, along B direction you can go to 1 by 3, and along C direction you can go to half, that is C by 2. So, if you consider this is a rhombus based prism. So, if we consider exactly middle point a rhombus, so here is one, this is one, this is one and this is one. So, this triangle if I divide into 2 halves, this rhombus if I divide, then I get 2 triangles, and if I take that 2 by 3, 1 by 3, 1 by 2, then one atom will be coming at this center point. So, this will be one atom. So, this atom will be coming or sitting on the 3 atoms here. So, here there is one atom, here there is one atom, here there is one atom. So, because this is the triangle, this triangle and this triangle are same. So, we have 2 identical triangles here. This is the lower plane, this is the middle plane, this is upper plane. So, this is A plane, this is B plane and this is C plane. So, we have got AB stacking. So, this actually it comes like this. So, we have got 3 coming here, these 3 are coming here and this one will be just sitting on that. So, that this is 1, 2, 3, if I call this one 4. So, this is, it will be in this form, it will be coming like this. So, 1, 2, 3. So, this 1, 2, 3 and the 4th one will be sitting on this. So, this is how it is formed. So, similarly, this same 4th one will be packed in on the triangle upper side. So, here also we will have 3, this is 1, this is 1 and this one. So, if you take this triangle, so this triangle and these 3 atoms will be packed inside on that. So, that this particular 4th atom will be in between 3 from lower this lower A stack A layer and 3 from upper A layer. So, this particular atom in the center, according to, because all these are hexagonally close packed 2-dimensional layers. Therefore, this one will have 6 contact points or 6 immediate neighbors in the same layer, 3 from lower layer and 3 from upper layer. So, therefore, coordination number in this case will be, coordination number is 12, because this any particular, the same is the case with any atom. So, because each lattice point is identical. So, we are just for convenience we take this particular small one that is Bravais lattice. So, in this case we see one atom in the B layer which is having 6 neighbors in the same layer which are in contact, along with the 3 from the bottom layer and 3 from the top layer. So, that the coordination number is 12. So, the number of atoms per unit cell when we analyze, here these corner atoms they will contribute 1 and there is one atom well within, that will be 2. So, the total then number of atoms per this Bravais lattice, this will be 2. So, this type of Bravais lattice having 2 atoms per unit cell or 2 atoms, they will be clubbed. So, 3 such Bravais lattice will be clubbed or packed in a tight manner, that gives this hexagonal close packed unit cell. So, hexagonal close packed unit cell, so in hexagonal close packed unit cell it will be having a shape of this kind. So, this is the approximate shape of the hexagonal close packed system, the unit cell of hexagonal close packed crystal structure. So, in this case all these are same distance, that is A or B, this is A is equal to B, A is equal to B, like that, and the vertical distance is C. So, this particular layer will come exactly along the middle region. So, if we carefully analyze, this is actually a combination of 3 hexagonal Bravais lattice. This is a combination of 3 hexagonal Bravais lattice with 2 atoms per unit per that cell. So, if we analyze, it is having a center point here also center. So, if we carefully do this, so this is one hexagonal Bravais lattice, this is another hexagonal Bravais lattice, and here the third one. So, we have got 3 hexagonal Bravais lattice. So, these type of 3 units are there inside. So, for the time being I will just take the middle region. If I take a middle, exactly the middle layer, then that will be having, if I so this is the middle layer. So, this is center point. So, this will be connected together and we will be getting all these are A, so this is 1, so we will be having 1 here. So, this form 1 lattice, 1 hexagonal Bravais lattice which is going down, and we have got another coming here and another coming here. So, this is 1, this one 2 and this one 3. So, there are 3 hexagonal Bravais lattice which are going downward. So, these 3 hexagonal Bravais lattice are tightly packed, and that is what we call it hexagonal close packed unit cell. So, inside if we divide this into 2, this is 2 triangles, this is 1 triangle and this is 1 triangle. So, there will be 6 identical triangles. So, these 2 triangles come inside one this hexagonal Bravais lattice unit cell. So, in that case, in one of these there will be an additional atom. So, this is the center region. So, here we will be having 1 atom, and the second one we will have again 1 here, and here also we will have 1. So, these 3 atoms will be attached, will be tightly packed with the bottom layer. So, that we will be having this upper layer and lower layer with middle layer will be tightly packed inside. Therefore, the total distance between 2 A layers is, that is A to A layer is C, and this is B layer. The center of these atoms is along the B, and that B layer will be at C by 2. A to B distance will be C by 2. So, this halfway. So, that is how we are getting this crystal, the unit cell of the hexagonally close packed crystal structure. Here, if we carefully analyze, then the number of atoms per hexagonal crystal structure. So, in the case of 1 hexagonal Bravais lattice, there are 2 atoms. So, here there are 3 such hexagonal Bravais lattice units. Therefore, number of atoms within will be 2. 2 into 3, that is equal to 6. So, we will have 6 atoms per unit cell. This can also be visualized in another way. If we take this particular point, then this point there are this another closed structure, that is a hexagonal close packed unit cell. Here there is coming another hexagonal close packed unit cell coming like this. That means one corner point, this particular atom is shared among 3 downward and 3 upward. So, total 6 unit cells are coming at this point. So, this particular, so if you visualize, so we have got 1 here and 1 below, and at the same time we have got 3 upward. So, this particular point is in contact with 6 unit cells, therefore, only 1/6 will be available in one particular unit cell. and therefore the total number is 1 6 into how many? 1 2 3 4 5 6 in the upper surface and 1 2 3 4 5 6 in the lower surface. Therefore the total number of corner points is equal to 12. Therefore 12 into 6, that is a contribution coming from corner point. Then this face center, this centered atom, this will be shared among one below and one above. Therefore only 1/2 will be available in one particular unit cell. Therefore here it is 1 by 2 into, there are 2 such atoms, therefore 2, plus these 3 will be coming well inside 1. These 3 will be coming well within, therefore there will be 3. So total you will be getting 2 plus 1 plus 3, that is equal to 6. So this way also we can calculate number of atoms per unit cell. Otherwise we can visualize there are 3 Bravais lattices inside, each having 2 atom per unit cell. Now we have to see certain other parameters, that is in the case of hexagonal Bravais lattice, our restriction is A is equal to B, A is equal to B, but not is equal to C. But in the case of hexagonal close packed crystal structure, there are certain restrictions. We cannot take any value for C. So here in the case of hexagonal close packed crystal structure, if we take that A layer and B layer, there will be 3 atoms which are in contact at the bottom layer, over which an atom from the second layer will be coming on this triangular void. So if we take these 3 atoms and the fourth one, all these 4 are in contact. So this distance will be A, because we are taking like this. This is our one point, this is another point, this is another point. This is A is equal to B and that is not equal to C. Therefore this distance is nothing but A, and this A is equal to 2R. Therefore A is equal to 2R. And this A, this is also A, this is also A. So we have a triangle, an equilateral triangle. So if we break this, so if we draw a perpendicular like this and like this, that is we are drawing a big triangle like this. This is an equilateral triangle. So this we draw here, here we are drawing, and here we are drawing. So in that case this is A by 2, this is also A by 2, this angle is 60 degree, therefore this angle is 30 degree. All these angles are 30 degree, and this angle is 90 degree, this angle is 30 degree, and therefore this angle is 60 degree. Because all these angles are identical, 60, 60, 60, 60 like that. So it is totally 360 degree. Therefore if we take cos A, suppose we want to find this distance I call it x. I want to find out this x. So cos 30 is equal to A by 2 divided by x, but at the same time cos 30 is equal to root 3 by 2. Therefore 2 cancel, and we will be getting x is equal to A divided by root 3. So this distance is A by root 3. Now on this we are placing the next unit here, that is from the next layer, that is B layer atom is coming there. Therefore that B layer atom is coming here, it is just above that, but this blue atom is in contact with A. Therefore the distance between the centers of A and blue atom, that is also exactly same A or B. Therefore we can say here we can consider another triangle, that is from here to here one side, from here to the center of the next one, that is C by 2, because B layer is exactly halfway between A layer and 2 A layers. Therefore this is one side is x, one side is C by 2 and the other side is A. So we will be getting another, because this blue atom is in contact with this. Therefore the centers will be, that is a hypotenuse, that will also be A. Therefore we will be getting a triangle, one side is x, one side is c by 2 and the other side is a. So, if we calculate this x is, we have already calculated, x is equal to a divided by root 3. Therefore, we can write a square is equal to a square by 3 plus c square by 4, or c square by 4 is equal to a square minus a square by 3, that is equal to 2a square by 3, 2 by 3 a square. Therefore, c square by 4 is equal to 2a square by 3, or c square by a square is equal to 8 by 3, or c by a is equal to root 8 by 3, which is 1.633. So, this c by a ratio, it should be root 8 by 3, 1.633. We cannot take any value for this c by a. So, there is a restriction, whereas in the case of hexagonal Bravais lattice, c by a can be any value. Only restriction is a is equal to b, not is equal to c. But here c by a is restricted to a value root 8 by 3, that is 1.633. That is one data which we have to note in the case of hexagonal closed packed Bravais lattice. Another point is we have to calculate the volume of the unit cell. So, to find the volume of the unit cell is equal to base area into height. So, we have got base area, base is in the form of a hexagon. So, this is your base and it is divided into 6 triangles, right. So, there are 6 triangles, therefore, base area into height means this area into height is c, because a is equal to b, not equal to c, and c is the distance between 2 a layers. Therefore, volume of this unit cell, is equal to base area into height. So, base area is nothing but area of 6 triangles. So, first we will calculate area of one triangle, that is we will calculate like this. So, this is our area. So, it is equal to half into base into height. Area of one triangle is half into base into height, that is here this is the base, all these distances are a unit. Therefore, this is a and this is height, therefore, this is equal to half into base is a into height we have to calculate. To find height h, we use this one right angle triangle. So, this is also a, therefore, this distance is a by 2. So, a by 2 h triangle. Therefore, we can write a square by 4 plus h square is equal to a square. Therefore, h square is equal to a square minus a square by 4, that is 3 by 4 a square. Therefore, h is equal to under root. So, h is equal to root 3 by 2 a. Therefore, we can substitute here root 3 by 2 a. Therefore, answer is half into base into altitude. Therefore, area of the triangle is equal to half 1 by 4 into a square into root 3. This is area of one triangle. Therefore, area of 6 triangles will be base area is equal to 6 times this particular value, that is 6 into 1 by 4 into a square into root 3. So, we can cancel this is 2, this is 3. So, 3 by 2 or 3 root 3, answer will be 3 root 3 a square by 2. 3 root 3 a square by 2. That is the base area. So that we can substitute here. So 3 root 3 a square 3 root 3 a square by 2 into the height. That is in the case of that unit cell hexagonal close packed unit cell, the height means it is the distance between A layers, that is equal to C. So this is the volume of unit cell. We calculated this volume of unit cell in order to calculate our atomic packing factor. So the next point is we have to calculate, because we said that this is a hexagonal close packed structure. So a hexagonal close packing comes when the packing factor is maximum or highest packing is obtained. So we have to ensure that that highest packing is possible in this distribution. So atomic packing factor is APF, that is equal to number of atoms per unit cell into volume of one atom. Volume of one atom is 4 by 3 pi r cube divided by volume of unit cell, that is 3 root 3 a square c by 2. 2 goes numerator and this 3 I take in the denominator. And we have already seen A is equal to 2R. So A is equal to 2R, therefore R is equal to A by 2. Therefore this R I am going to replace, this R I will replace with R is equal to A by 2 into A by 2 into A by 2. So I will be able to cancel this 2 and this 4 and this A square and this A square. And N is number of atoms per unit cell, which we had seen 6. So for N also I am just replacing, I put it 6 here. So if I cancel this 3 and this 6, then this will be 2. Therefore you will be getting 2 pi divided by 3 root 3 into A by C. But C by A is root 8 by 3. Therefore A by C is root 3 by 8. So this A by C I am going to replace with this one. So A by C is equal to root 3 by 8. By 8 I write it as 2 into 4. So from that 2 into 4 I will be taking 4 out. So this will be 2 coming out. Then this 2 and this 2 will be cancelled and this root 3 and this root 3 will be cancelled. So this is equal to pi divided by 3 root 2 and this is equal to, if you calculate, this will be 74%. That is, in the case of hexagonal close packed crystal structure, we will be getting the highest packing just like your face centered cubic system, and this is a maximum we can expect in the case of this hard sphere packing model. So we have already seen this C by A ratio, we have seen the volume of the unit cell, we have seen number of atoms per unit cell in the case of hexagonal close packed structure, and etc. So more on these other crystal structures we will see in the forthcoming lecture. Thank you.